Good morning, everyone.
Good morning, sir.
Good morning, everyone. So,
Good morning, sir.
good morning, everyone. So, chaliye, welcome to the Geography Revision course. So, as we have discussed earlier, okay, in this course, basically we are looking forward to complete whole of the geography revision in 15 to 16 sessions. Okay, and each session would be 2 hours each. Okay, the schedule we are going to have on Saturday 2 classes, on Sundays 2 classes. So every week 4 classes would be there. So roughly 4 to 5 weeks, this is our target where we would be able to complete the revision of whole of the geography. So overall, in this case, the first how you are going to utilize the course basically is where uh, what we will see is in your group also, I have shared with you guys the notes as such. So overall, with respect to these classes, the first thing that we would see would be these handwritten notes which are there. Now, these handwritten notes, they are going to serve you is basically with these are short notes with, let's say, 7 to 8 pages, 10 pages, one chapter over. Okay, and these are the notes that you can directly utilize for your revision just before the examination. So all the necessary details which are there, okay, are given in these notes. Secondly, apart from that, for the sessions, we are going to have these practice questions. And in these practice questions, we have included the PYQs also, the previous year questions from that particular section. So previous year questions we are going to discuss in the class also. But now your task would be after the completion of the session, you make sure that you have attempted all the practice questions so that we can clarify any doubt with regards to these practice questions in the next session itself. So this would be a deal where we say at this particular point of time, definitely you guys would be busy in a lot of things, including completion of your other parts of geography syllabus, the GS syllabus, which is there. Okay, but the idea of launching this particular course is where if you just dedicate your 2 days on weekends for this particular subject within a month or month and a half, you would have completed geography completely. So for the remaining 5 days, you can go on with whatever you are doing with other subjects of GS. And Saturdays and Sundays, if you dedicate to geography, within 1 month or 1.5 months, we would be able to complete this particular section. Okay, about the running notes and all, it's up to you. Okay, if you want to take running notes, you can take. Otherwise, it's given over here in the short notes. So your idea is basically to sit back, relax, and try to understand the things, grasp the things. Well, this is now the revision time. You should have a very clear-cut idea of what is being talked about. And when we come to the questions, how the questions have to be tackled. That is what we have to learn. So before the start of the course, anyone wants to ask any question? Whatever are the aspects related to current affairs, related to the geography, we would integrate it in the detailings itself, in the respective portions. So that would be integrated within this. Yes, anyone else having any doubt? Any question to ask, clarify? Chaliye, okay. So everyone just save that notes that I have shared with you so that you can keep referring to that. We would refer to the notes. So let's start with the topics now. First chapter we are going to start with is geomorphology. Now, geomorphology, if we want to understand from the perspective of geomorphology, last 15 years, if I see, in the last 15 years, I would not say more than 10, 15 questions have been asked from this particular section. So this is from prelims perspective, geomorphology is not something where we need to go into too much of detailings. Okay, yet we need to have a basic idea and we have to understand what type of questions UPSC is asking from this particular section. So first we are starting with geomorphology. And the topics for today's discussion for us, okay, are the first we are going to start with the interiors of the earth, study of interiors of the earth. The second one about the distribution of oceans and continents in the form of continental drift theory, seafloor spreading, and plate tectonics most importantly. So these are the topics today we are trying to cover and complete, of course. So first we are starting with the interiors of the earth. So when we talk about the interiors of the earth, what about interiors of earth? First thing, that is in the case of interiors of earth, studying the interiors of earth, there can be some direct methods, there can be some indirect methods or indirect sources. So direct sources and indirect sources. Direct sources is where you observe something directly. What is there in the interiors of earth, we observe it directly. And what can be that direct source? So direct source, when we say the direct sources would be including, let's say, for example, drilling. So you are drilling the earth, and in the interiors with the drill, you can very easily figure out, directly observe the rocks, okay, their properties, the temperature, the pressure, the density of the rocks which are there. So it's where you drill the earth and you observe it directly. That's the direct evidence. Apart from drilling, you can have volcanic eruption. So with volcanic eruption, the magma as it comes out from the interior, so we can study the magma directly, and from there I can figure out that what lies in the interiors of the earth. So there are certain direct sources which are there, but with direct sources, the challenge which is there is that the access to the interiors of earth for us is not that much, which means the drilling when you do. With the drilling, there is a limit up to which drilling can be done. Now this limit up to which drilling can be done, if I take an example of this drilling, so there was this project called as Kola Superwell project. Kola Superwell project, this Kola Superwell, Kola Peninsula. Kola Peninsula lies where? Kola Peninsula is in northwestern Russia. Kola Peninsula. Okay, and in that Kola Peninsula, there was this deep drilling project which was undertaken. Its whole sole purpose was to study the interiors of the earth itself. But with the disintegration of USSR, the project was abandoned. But nevertheless, okay, they were able to dig up to 11, 12 kilometers. And after that, the project had to be abandoned because the temperatures were extremely high at that depth only, 12 kilometers depth. The temperatures were extremely high. The pressure was extremely high. The instruments that they were using, they stopped working. So that's where we see that there is a limit with respect to direct observation. Okay, what you can observe about the interiors of the earth. So the geologists are more dependent on indirect sources. Indirect sources, basically with respect to indirect sources, if I see, so indirect sources, under that the first comes, which is the patterns of change in temperature, pressure, or density. So as we go deeper, the temperature goes on increasing, the pressure goes on increasing, or the density goes on increasing. What we can do is we can figure out the initial rate of changes of these parameters. And if you know the rate of change of these parameters, you will be able to calculate the temperature, pressure, or density at any depth. But that would be purely done on the papers. You have no direct observed data with respect to that. So this is where on the papers you can calculate the conditions of the interiors. That's one thing of the indirect sources. Apart from that, the other one being the different parameters related to the Earth's interior, which may include, take for instance, the gravitational field. The study of gravitational field. Now, the gravitational force at different points on the Earth would be different. And that gravitational force would be purely dependent on the mass of the material underneath it. So you have the Earth, if you are talking about the gravitational field at this point, whatever is the mass of the material underneath this, up to the center of the Earth, this mass is going to impact the gravitational field. Plus, we know the shape of the Earth is not perfectly sphere, but rather oblate spheroid, a slight bulge. The radius of Earth at different points is also different. All of this results in differences in gravitational field at different points or at different places. So studying the variations in these gravitational field is going to give me an idea of the materials underneath that particular place. Because mass ultimately is going to depend on density, correct? So density is more, density is less. This is how we can figure out. So changes in the gravitational field. Very much similar to that, we can deal with the changes in the magnetic field, the variations in the magnetic field. A magnetic field, the magnetism of the Earth. The magnetism of the Earth emanates from the core of the Earth. So the arrangement between outer core and inner core, this results in the magnetism of the Earth. So with this magnetism of the Earth, as the magnetic fields, so emanating from here, as the magnetic fields pass through the interiors of Earth, their properties do change. And what we can do is we can study the magnetic field over here. If I study the magnetic field that I'm getting over here, this magnetic field is going to depend upon what material is over here. So again, the idea that at different places I'm going to study the magnetic field, I'll be able to figure out that what is the material underneath this particular place. Okay, it's pretty much like you have, let's say, for example, a magnetic field source over here, which is generating a magnetic field. You have some material over here, let's say a slab. So magnetic field originating from here, if you get the magnetic field over here, you'll see that the magnetic field that you are receiving here would be different from what was emanating from the source. Because this magnetic field has passed through some sort of material. The property of material would have changed the property of the magnetic field itself. Correct, everyone? So the study in the variations of magnetic field at different places, this also can be an indirect source. But most importantly, and most reliable indirect source that the geologists use is the study of seismic waves. Study of seismic waves. So study of seismic waves are what? The waves related to earthquake, the energy released from earthquake. Seismicity is the word that we use for earthquakes. So studying the earthquake waves, so we would be able to study the interiors of the earth. So if you now see in your notes, this is one particular part that you will find. And what is that part? Here, the first thing that we have given is under the interiors of the earth, sources, direct sources, indirect sources. Correct. Under direct sources, we have written mining, drilling, volcanic eruption. Correct. These would be direct sources. And then we have indirect sources, which are patterns of changes in temperature, pressure, and density, gravitational field, magnetic field, seismology. Meteors is one that is indirect source, study of meteors. type of question from this particular part is nothing but purely the question like which of the following are direct sources of study of Earth's interior. You will be given a list. So the first question comes from here itself. That would be sources of study of Earth's interior. Got my point? So you can note it down, question 1. We are not writing the question, we would be just writing the topics which are there. Question 1, and put a hyphen. Yes, Aryan, please.
So someone has texted in the group that they are waiting in the meeting.
Wait. Acha, okay. Thank you. Yes, so question 1 would be listing, mention there, listing direct and indirect sources. Listing direct and indirect sources of study of Earth's interior. Of a study of Earth's interiors. So this is the first topic. Now from here, let's try to understand the seismology. So seismology, how it helps us to determine the interiors of the Earth. So with respect to seismology, what we see is first thing, the seismic waves. Seismic waves are the waves related to the Earth's interiors. And now in case of Earth's interior, what we find is the earthquakes when occurring, the actual point of release of energy from the earthquake. This is the point that we call as the focus of the earthquake. Now from this focus, as the energy is released, this energy propagates in all the directions in the form of waves. And so we have the waves which would be moving like this. These are the first one which are called as body waves. They are traveling through the interiors of the Earth. First thing. Secondly, apart from that, now as the waves, these body waves reach the surface of the Earth, these waves are able to interact with the rocks over here. So when these body waves interact with the rocks of the lithosphere, they give rise to another set of waves now which travel along the surface, and these are the ones that we call as surface waves. So we have body waves, we have surface waves. Body waves travel through the interiors of the Earth, surface wave travels on the surface of the Earth. Two set of waves. Now here, this is the point which I call as focus. This is the point which I call as epicenter, which is right above the focus point. So seismic waves, two categories, body waves, surface waves. And so in this case now, when we talk about these body waves and surface waves, what I can see very straightforward is first of all the difference between these two. That is the first thing that we have to know. So first we are talking about these body waves, and in case of body waves, what we see is body waves can be of two different types, which are P waves and S waves. Now P waves and S waves, P waves are primary waves. S waves are secondary waves. So primary waves, secondary waves. These are secondary waves, or another name that we use of these is shear waves. So any of these can be used, secondary waves or shear waves. Now, primary waves and secondary waves, what's the basic idea over here? Would be the differences if I see. The first one is, as the name suggests, primary and secondary. It means what? When from the focus these two waves start, one wave travels faster and reaches the surface first. These waves which reach the surface first, they are called as primary. Primary because they are being received first. And after a while, the second set of waves will be received. So two waves are traveling from the focus. As it reaches over here, there is this wave which reaches over here first, that is P waves. And after that, another set of waves is traveling a little bit slower, and so would be received after a while. And so these would become S waves. So primary and secondary waves. So with these primary and secondary waves, what would be the first point of difference? First point of difference would be in terms of their speed. Which one is faster? Yes. Which one is faster?
P waves.
P waves.
P waves are faster. So I can say these waves are faster, these waves are slow.
Slower.
Correct? So faster and slower. This is the first difference. Apart from this, the second one is the nature of these waves only. Now, nature of these waves, the P waves we identify as longitudinal waves. And S waves we identify as transverse waves. Longitudinal waves, transverse waves. Now, what are these waves? With respect to longitudinal waves, if I see, what do we mean by longitudinal waves? So when the waves, if this is the source, now what is going to happen? From this source, the waves are going to travel outwards. Okay, let's say for example, yahan se. This is how we show the propagation of the waves. You may have seen this in case of sound, जब हम sound show करते हैं. So in the case of sound, we can show it like this. Or these days, it is used to show Wi-Fi, correct? Wi-Fi signal भी ऐसा ही दिखता है. Wi-Fi signal is what? It is nothing again but waves. So waves are propagating like this. This is how we show it. So this is the source and this is the destination, let's say, for the wave. So if I have to say direction of propagation, propagation is where the waves are moving. So direction of propagation, if I have to say, can I say direction of propagation of the wave is this? Source to destination. This is the direction of propagation of the wave. So when we say longitudinal or transverse, the idea is, in case of this direction of propagation, if I identify as this, the particles in this particular case of longitudinal waves vibrate like this. This is the direction of vibration. Okay, which means in this case, the particles vibrate in the direction of propagation of wave. So take for instance sound waves. When I say, okay, I'm standing over here, there is this camera, I'm speaking, the sound is reaching over there, let's say you. So as I speak, reaching to you, this is the direction of propagation. How the air is vibrating basically over here, the molecules of the air is, when I speak, the molecules are pushed forward. And then due to elasticity, they come back. Then again push, come back, push, come back. So the direction is like this, correct? This is what is longitudinal wave. So in case of longitudinal waves, what we can say? Longitudinal waves would mean over here that the particles of the medium vibrate to and fro along the direction of propagation. So over here, longitudinal, I'll say vibration along direction of propagation. One example over here is sound waves. On the other hand, transverse waves. Transverse waves, in the case of transverse waves now, the direction of vibration, again, if this is direction of propagation, the particles vibrate like this. That is perpendicular to the direction of propagation. So vibration perpendicular to direction of propagation. And so this is the nature of the two waves. The P waves are longitudinal in nature, whereas S waves are transverse in nature. Along with that, another important difference is in terms of the medium through which these waves pass. And more importantly over here, P waves can pass only through solids. Sorry, P waves can pass through all the mediums. S waves can pass only through solids. So if there is any liquid medium, if there is any molten medium, okay, the S waves would not be able to pass through it, but P waves still would be able to pass through it. These are the three basic points of difference between P waves and S waves. And along with this, we have a common property with respect to any of these waves, and that common property for us is with respect to velocity of these waves, where we say that the velocity of these waves is directly proportional to density of medium. Density of medium. So the more dense the medium is, the faster the waves are going to travel. It is applicable to both P waves as well as S waves, for both the waves. Yes, Maniket, please.
Sir, in the notes, it is written that P waves traveled only through solids and S waves
Right,
travel.
so that's the correction. That's the correction. Okay. There's by mistake it has been written. That's the opposite. P waves pass through all the medium, S waves only through solids. Yes, Nivedita.
So this factor, like that P waves are faster and S waves are slower. And while when the waves will pass through any medium, they'll be more faster. So these two factors are independent of each other. Right?
Yes, these two factors are independent of each other. First thing, velocity is directly proportional to density of medium. That is applicable to all the waves. First thing. So if you just take P waves or if you just take S waves and make them pass through different mediums, okay, a S wave would be traveling faster in a denser medium than a rarer medium. But if you keep the medium similar and compare P waves and S waves, P waves would be faster in that. So these are the differences in properties of P waves and S waves. Okay, so body waves. After body waves, the next one that we have are surface waves. Surface waves, although not directly related to studying the interiors of the earth, but yet, okay, we are going to look at just their property. So when we talk about the surface waves, in case of surface waves, what we can find is two types of waves. The first one, which is called as Rayleigh waves, and second one, which is called as Love waves. So Rayleigh waves and Love waves. Here again, the difference lies with respect to the direction of vibration. How the direction of vibration is there? Rayleigh waves, in this case, if the direction of propagation is like this, the particles over here vibrate in this pattern, which is perpendicular to the direction of propagation. But what is the basic difference? So everyone see over here, if this was the direction of propagation, this is the direction of propagation. In this case, when we say transverse waves, that is S waves, in that case, the particles will vibrate like this, up, down. Correct? So if you see over here, this is the direction of propagation. This is the vibration direction, perpendicular hai. Correct, everyone? Rayleigh waves mein, this is the direction of propagation. Particles would vibrate like this. So still it is vibrating on this plane only, but not just up and down, but slightly like this. So perpendicular abhi bhi hai. Correct, everyone? So still it is perpendicular, but on a plane rather than just up and down. That is Rayleigh waves. On the other hand, love waves. Love waves mein direction of propagation is this. So the vibration is taking place like this. Now what is this? अब देखिए, यह है direction of propagation. Now the particles are going to vibrate like this. Or from this direction it would be clearly visible. This is direction of propagation. The particles are going to vibrate in this pattern. अभी भी perpendicular है. तो आप देखिए, अगर आप तो ट्रांसवर्स वेव में कैसा वाइब्रेशन हो रहा है. एवरीवन होल्ड योर हैंड लाइक दिस. होल्ड योर हैंड लाइक दिस. हाँ, एंड नाउ शो मी फर्स्ट in front of the camera. Hold the hand, and now from the other hand just show me the vibration. First I am asking about the S waves. What is the vibration? S wave. S wave is up and down. Correct. S wave is up and down. Rayleigh wave, yes, around it. And love waves, sideways. Got it, everyone? Remember it? So in all these three cases, what I can see is the direction of propagation and the vibration of particles. What is the angle between them? In all these three cases, 90 degree. Just now you have done like this or like this or like this. Everything is 90 degree only. So out of the 4 waves that we have now, okay, that is the P waves, S waves, Rayleigh waves and love waves. 3 waves are there in which particles vibrate perpendicular to direction of propagation, and there is 1 wave in which the particles vibrate parallel to the direction of propagation. Understood, everyone? These are the properties of seismic waves. And this is your second question. So question 2, just note down. See, on a paper you will keep this as a separate list. एक separate paper पे you'll just mention कि what are the possible questions or areas. So question 2 would be properties of seismic waves. Properties of seismic waves. Yes, done. So overall, in this case, now the body waves are used to study the interiors of the Earth. And as the body waves pass through the interiors of the Earth, these body waves are received. Seismograph plots a graph, and based on that, the scientists deduce what lies in the interiors. So over here comes up this particular concept of shadow zone. Now, shadow zone. What do we understand by shadow zone? So for shadow zone, if you want to see, a basic idea of shadow zone is, if this is the focus let's say center of the earth, and I have certain layers over here. So in the interiors of earth, we have a crust mantle core. Core mein I have inner core, outer core, in which outer core we know is in liquid form. We'll see it later also under interiors of earth. But as of now, this layer is liquid or molten. So what happens first, if I talk about the P waves or S waves, first of all. So S waves, right there from focus starting, the S waves are passing through like this over here. But if you see the S wave reaching here, it would not be able to pass further, because we have said that S waves can pass only through solids. So S waves cannot pass from here now. Likewise, S wave coming over here, it would not be able to pass through from here. So these S waves would be blocked. Maximum the S wave would be able to pass, which would be tangential to this. Maximum this much. Beyond this, in this particular part, no S wave would be able to allowed to pass through, because the liquid barrier would be there, the molten barrier would be there. Which means right there from here to here, this whole region is where you are not going to receive any S waves. And this is the concept where we come across this idea of what we call as S shadow zone. So the shadow zone is where we receive no such waves. You call S shadow zone right now. इसके बाद P shadow zone की बात करेंगे. Okay, but in this zone, S waves are not received. And as a fact, you have to memorize it for the paper. That is, the S shadow zone extends beyond 105 degrees. So 105 degrees from all the sides. This angle is measured like this. Focus to center, and from here. This is 105 degrees. So between 105 degrees, there lies this what we call as S shadow zone. Then apart from that, we have the P waves. So when we talk about the P waves now, what about the P waves? So in case of P waves, what I can see again, P waves can pass through from here throughout. Now as the P waves reach here, let's say this is the P wave we are talking about. Now the P wave reaching over here, P wave can pass through all the mediums, correct? But what is going to happen is, as the P wave is going to pass from this solid to this molten or liquid medium, the medium changes, the density changes. So it is going to undergo a lot of refraction. Refraction, we understand? Bending. Okay, in schools we have studied this particular type of diagram. Glass is there, okay, light falling on it, and it bends like this. So as the waves pass from one medium to another medium of different densities, it bends. That's refraction. And the same thing is going to happen over here, solid to liquid. So from here it bends like this. Again, it passes from liquid to solid. Inner core is solid. Again bends like this. Again bends and again bends and comes out. Over here, the same thing is going to happen. So, and in between that, whatever waves are there, we are going to get simply all the waves over here. Okay. So you are going to get all the waves here. But what about this zone? This is a zone where now I am not receiving any P waves, because all the P waves have been refracted completely. And so this zone between 105 degree and this becomes 145 degrees. So between 105 degrees and 145 degrees, no P waves are received, and this is called as P shadow zone. So we have P shadow zone, S shadow zone. S shadow zone, what is the extent of S shadow zone? S shadow zone is beyond 105 degrees on all the sides. P shadow zone is between 105 and 145 degrees. These are P shadow zone and X shadow zone, S shadow zone. Now in this case, one concept comes, which is absolute shadow zone. Now when you say absolute shadow zone, what should we mean by that? Absolute shadow zone should mean the zone where no waves are received, neither P waves nor S waves. So in this case, if I have to mark these zones, S shadow zone mark करते हैं. S shadow zone पूरा ये S shadow zone है. Correct. Is it the case that it is completely empty? No. In this zone, यहां हमें P waves मिल रही हैं. I'm getting P waves. So I cannot call it absolute shadow zone. But now if I talk about the P shadow zone, P shadow zone ये है. Are you getting any waves over here? P or S? No, none. Neither P waves nor S waves are being received over here. So which one, P shadow zone or S shadow zone, I should call as absolute shadow zone?
P shadow zone.
P shadow zone. And so this is a fact that you have to know. P shadow zone would be absolute shadow zone. Note down in your running notes. P shadow zone is absolute shadow zone. As neither P waves nor S waves, neither P waves nor S waves are received here. Neither P waves nor S waves are received here. Now, after this, absolute shadow zone. Akash, absolute shadow zone you have not understood.
Yes,
See,
sir. Yes.
absolute shadow zone means a zone where none of the waves are going to be received. So if I now say the S shadow zone, S shadow zone, how S shadow zone will look like? S shadow zone will look like this and this. Correct? This is 105 degree or 105 degrees, let's say. ये S shadow zone है. Now, is this a zone where no waves are received? No, not. See, P waves are received over here. P waves are received where? P waves are received in this zone. यहाँ तो P waves मिल रही हैं.
Yes, sir.
So then I cannot call this whole zone as absolute shadow zone.
Hmm.
But this is P shadow zone. Correct?
Yes.
Can you see any waves here?
No.
No.
Yes.
Neither P waves nor
Yes,
S
no.
waves.
Yes.
So that's where I call it absolute shadow zone.
Shadow zone. Okay. Okay. Got it. Got it.
So we have the P shadow zone as absolute shadow zone. Now, based on this, when we talk about the interiors of the earth or internal structure of the earth, what lies in the interiors of the earth? So overall, interiors of earth, what can be done is the interiors of earth can be divided or identified based on two major factors. The first one that we identify, that is based on chemical composition. Based on chemical composition. And so based on chemical composition, we have crust, mantle, and core. Crust, mantle, and core. Okay, now question 3, you will just mention over there shadow zones. Question 3 is shadow zone. Crust, mantle, and core. Now, crust, mantle, and core, in this case, first when we talk about the crust. So overall, crust is the outermost layer of the earth, first thing. And on the surface, whatever we see, that is all crust. So when we talk about the crust, on the surface, I can divide the crust into two different types. One which I call as continental crust, another which I call as oceanic crust. So we have continental crust, we have oceanic crust. Now continental crust, oceanic crust, the difference between them. That's the next question. So mention the next question beforehand itself. Next question. Difference between continental and oceanic crust. Difference between continental and oceanic crust. The difference between continental and oceanic crust, the first thing is about the thickness itself. What I see is, if we talk about the difference in terms of thickness, how it is going to look like would be something like this. This represents continental crust, this represents oceanic crust. Differences is given in your notes. So just try to understand it. Continental crust, oceanic crust. Continental crust is thicker. Oceanic crust is thin. That's one thing. So when we say average thickness of continental crust goes up to 30-35 kilometers. Oceanic crust ki average thickness is in the range of 5 to 8 kilometers. So obviously there is a significant difference in terms of thickness of the continental and oceanic crust. That's one thing. In addition to that, the difference also lies chemically. That is the minerals and the rocks from which these are made. Wherein continental crust we mainly identify with andesite or granite. Okay, more close to andesite. So we say continental crust is andesitic, whereas oceanic crust is basalt. Now, basalt is mainly derived from the cooling and solidification of magma. And that's how majority of the oceanic crusts are formed. So oceanic crust is basaltic in nature. Continental crust is andesitic in nature or granitic in nature. And a direct result of this difference, chemical difference between the two crusts, comes in the form of their density, where continental crust is light, whereas oceanic crust is dense and heavy. So that's the basic difference that I find between oceanic crust and continental crust. Okay, everyone? That's the first difference. Apart from that, going beyond that now, when we talk about the mantle. So below the crust lies mantle. And mantle extends up to 2,900 kilometers depth. Jahan mantle ko we divide it into अपर मैंटल, लोअर मैंटल। अब डीलिंग विद द मैंटल, यहां मैंटल में द डेंसिटी ऑफ द रॉक्स ऑफ कोर्स वुड बी मोर देन दैट ऑफ क्रस्ट, और यहां पे हमें आयरन, मैग्नीशियम, इनके सिलिकेट्स मिलते हैं इन टर्म्स ऑफ मिनरल्स। अगर आप क्रस्ट में देखिएगा तो सिलिकॉन, एल्यूमिनियम विच वी कॉल एज सियाल, दैट वुड बी मोर प्रोमिनेंट क्रस्ट में। मैंटल इज also was earlier identified as सीमा लेयर। यहां सिलिकॉन तो ओके कॉमन है, मैग्नीशियम। सो मैंटल में वी मेनली गेट द सिलिकेट्स ऑफ आयरन एंड मैग्नीशियम, और मिनरल्स जो होते हैं हेवी मिनरल्स मिलते हैं। सम एग्जांपल्स ऑफ दीज हेवियर मिनरल्स इंक्लूड ओलिवाइन, पायरोक्सिन। सो दीज आर द मिनरल्स which are found. Basically, I have to know that over here the minerals are heavier, and these names, olivine, pyroxene, and all. Now, mantle occupies maximum volume in the Earth's interior, disproportionately higher volume in the Earth's interior. And most importantly, mantle, including upper mantle, lower mantle, mantle is mainly from where majority of the volcanic eruption is sourced. So the magma is mainly sourced from mantle. And then we have core. Core may we have the outer core and inner core. So अब यहाँ पे if you see here, or first let me tell you about this outer core and inner core. So when we say outer core and inner core, यहाँ पे I have inner core and we have outer core. So over here in this case, outer core is in liquid form or molten form. Core is mainly made up of iron and nickel. Both outer core and inner core. But the difference is where outer core is in molten form, inner core is in solid form. Why is it so basically? So over here molten and solid. Why this is so is mainly because of the relationship or relative strength of temperature and pressure. Now try to understand this point. Pressure. Whenever you are increasing the pressure, in that case, what is going to happen is the melting point also increases. Because if you see solids are arranged like this, liquids are arranged like this. Correct? But if I put a lot of pressure over here on this, I'll not allow this to loosen. Going from this solid to liquid, it's like loosening of the bonds between the molecules. But if I put a lot of pressure, I'll not allow the bonds to loosen. And so melting point increases. So if I say something is solid, at high temperatures we are saying, at high temperatures, even at high temperatures, if something is solid, what would it mean? That pressure is very high. Pressure is not allowing it to melt. So if it is solid, I'll say pressure is very high. And if it is liquid, I'll say pressure is not sufficiently high. So the idea is temperature and pressure, which one is dominating? अगर टेम्परेचर डोमिनेट कर जाएगा तो क्या स्टेट मिलना चाहिए मुझे?
Liquid.
Liquid. If the temperature is dominating, I should get liquid. If the pressure is dominating, pressure will not allow it to melt, even at high temperatures. And so I'll get solid. So over here, if I ask you why outer core is in liquid form? Because
Less pressure.
pressure is not sufficiently high. Temperature is very high, but pressure is not sufficiently high to keep it in solid form. But if I say inner core is solid, iska matlab pressure is very high and pressure is not allowing it to melt, although temperature बहुत high है inner core में. Still it does not melt. ठीक है, so when we say outer core is in molten form, there are two reasons over here. Outer core is in molten form. What would be the first? Just now you have told outer core is in molten form. Why? Because pressure is not sufficiently high to check the melting. ये first reason है. Second reason है that in the outer core, the iron and nickel which is there, it is mixed with some silicon. यहाँ silicon भी present है. Some amount. Traces of silicon are present over here in outer core. When the silicon is present, it overall decreases the melting point. That's why here I call it as silicon impurity. That in outer core, there is the presence of silicon impurity. So these presence of silicon impurities reduces overall melting point. And that's where, okay, we find it in molten form. So two reasons why outer core is in molten form. Okay? Now question can be anything. Question would be in terms of the state of the inner layers. और क्वेश्चन वही होगा. अब अगर if I ask, put a question like this to you, कि although the temperature in the lower mantle is very high, yet it is in solid form. Why? Tell me, Jareen.
Sir, am I audible, sir?
Yeah, you are audible, please.
Sir, can you repeat the question, sir?
Yes, the question is, although the temperature in the lower mantle is very high, yet it is in solid form. Why?
So because of the pressure.
Absolutely, yes. The answer remains same. Let them ask any layer. Okay, I told you the shortcut. If it is solid, it means pressure dominates. If it is liquid, it means pressure is not sufficiently high, temperature dominates. Got my point? So this would be your next question. Right there, next question. In that question, just mention that despite having very high temperature, comma, any layer in the interiors does not melt due to high pressure. Due to high pressure. And next question, one more question put there. Next question, why outer core is liquid? Why outer core is liquid/molten? Yes, okay, everyone. So this is now for you the interiors of the crust, mantle, and core. Ab, apart from that, so over here, if I see these layers, what I can check? Crust. This is the first part, that is crust, and in the crust you can see this part should represent OC, this part should represent CC, oceanic crust, continental crust, correct everyone? So oceanic crust, continental crust, that's the first part. Then I have upper mantle, lower mantle, and then we have outer core, inner core. The limits of depth over here is 2,900 kilometers, 5,100 kilometers. And then you have 6,371 kilometers, which is the mean radius of the Earth. Then in addition to that, we have the boundary between different layers. And these boundaries between different layers, they are called as the discontinuities. Simple, nothing, boundary between two layers. These boundary between different layers, they have been given certain names. Okay, right there, starting from Conrad discontinuity in your notes, I have given you the list. So no issues absolutely in that. So on first discontinuity that you have is Conrad discontinuity. Conrad discontinuity upper crust, lower crust को separate करता है. Then we have second, that is Moho discontinuity or Mohorovičić discontinuity. Okay, यहाँ पे crust और mantle separate हो रहा है. Likewise, third is Repeti between upper mantle, lower mantle. Okay, then we have Gutenberg discontinuity, fourth, between lower mantle and outer core. And last one that we have is Lehman discontinuity between outer core and inner core. Got it, everyone? So these are discontinuities. So discontinuities name we have to remember very clearly. So next question just mentioned there, name of discontinuities. Under the question list, next question, name of discontinuities.
Sir,
Name of, yes, please.
so what is the difference between upper crust and lower crust?
Upper crust and lower crust, the basic difference in terms of density only.
All right.
Okay, upper crust is less dense, lower crust is more dense. Anyways, as you go deeper, the density increases.
Yes, sir.
Secondly, in their composition itself, pretty much like continental or crust, oceanic crust, we differentiate. Upper crust is mainly granitic, lower crust is basaltic.
All right, sir.
And we have done that granite is less dense than basalt, basalt is more dense. So this is where the first level of classification comes up, which is based on chemical composition. After this chemical composition, the next one that we check is what is called as based on mechanical rigidity. Another level of classification based on mechanical rigidity. So based on mechanical rigidity, now what do I have is 4 layers, that is lithosphere, asthenosphere, mesosphere, and barysphere. These are the 4 layers. Okay, in this, I can study it from this particular diagram. So over here in this diagram, everyone check here. When we talk about crust, mantle, now what happens is right there from here up to here, which means effectively crust thickness is, let's say continental crust, we have said average thickness is 30-35. At certain places it can go 70 kilometers, 100 kilometers, like Himalayas, very thick crust which is there. So it may be there. Overall, I am taking this roughly, let's say up to 200 kilometers. So right there from the surface up to 200 kilometers. This is the topmost part, which is very cold and very brittle. Brittle means it breaks very easily. So यहाँ पे up to this part, okay, 200 kilometer. This is the first part that I identify as lithosphere. Lithosphere, brittle, cold and brittle. इसके बाद from here, from 200 to roughly up to 700. This is now the most important layer. And what is this layer? This is the layer which is in semi-molten state. Semi-molten state, और इसको हम प्लास्टिक स्टेट कहते हैं. अब ये सेमी मॉल्टन या प्लास्टिक क्यों है? अगेन वेरी इंपॉर्टेंट. ओके, इट इज सेमी मॉल्टन और प्लास्टिक स्टेट. सो प्लास्टिक स्टेट में है ये. एंड व्हाई इट इज इन प्लास्टिक स्टेट? फर्स्ट, because of radioactivity, radioactive material present over here. Okay, and apart from radioactive material, okay, another one is the residual heat. Residual heat mainly means when the earth cooled down and solidified, some of the heat is still trapped in the interiors. Earth was very hot in the beginning, and that's called as residual heat. तो यहाँ कुछ रेसिडुअल हीट है इंटीरियर्स में, along with that radioactive materials, and due to which all the heat generated has melted this layer. Not completely, partial melting. So it's like a jelly-like state. Compressible, most importantly. तो यहाँ प्लास्टिक स्टेट है, कंप्रेसिबल है. And that's called as asthenosphere. So lithosphere and then you have asthenosphere. इसके बाद रेस्ट इज यहां से यहां पूरा मैंटल जो बचता है. This is what we call as a mesosphere, and then whole of the core, this is called as barysphere. So based on mechanical rigidity, we have 4 layers over here. What are these? Lithosphere, asthenosphere, mesosphere, and barysphere. So tell me now, okay, if just let's see from examination perspective, what should we know straightforward. First thing, if I talk about lithosphere, lithosphere comprises of what? Which layers?
The crust and uppermost mantle.
Absolutely, crust, and I'll put it like parts of upper mantle. It is going to extend through upper mantle क्योंकि इसका पूरा thickness 200 किलोमीटर है. Crust की thickness तो 200 किलोमीटर it never reaches. So definitely some part of upper mantle also would be included under lithosphere. Asthenosphere extends through what layer? Only upper mantle. In the diagram I can see asthenosphere lies completely within upper mantle. Correct, got it? So this is now the layering of the earth based on what? Mechanical rigidity. How rigid are the rocks? So now under questions list, mention next question. Under questions list, mention the next question. Extent of lithosphere and extent of lithosphere and asthenosphere. Extent of lithosphere and asthenosphere. And next question, why asthenosphere in semi-molten state? Why asthenosphere in semi-molten state? Done, everyone? So this is the list of the questions that can come from this particular section. See, the list of the question is most important. Okay, the ultimate thing that you have to do is you have to go through a list of the questions. You have to make sure you know about that particular topic. And if you know about that topic, okay, highly unlikely that any question will go out of the list that I'm going to give you. So ultimately, this is the list from where all the questions most probably have to come in the examination. Most probably, always we are going to add. So first topic, interiors of Earth. This is the interiors of Earth, internal structure of Earth, seismology, everything. So can we move to next topic, everyone? Comfortable with this? This is all what is relevant for the prelims. We are focusing on prelims examination. Whatever is relevant, I'm giving you the question list also based on that. So next topic. Next topic is very less relevant for prelims examination. Yet there are few things that I would like you to remember in case. So the next one is continental drift theory. So with continental drift theory, what we can see is continental drift theory was given by Alfred Wegener. Wegener gave this theory, and in this theory, basically, Wegener has talked about how the continents have moved over the period of time, and the present day positions of the continents have been explained. That's why continental drift, continents have drifted. So what Wegener hypothesizes is that at some point of time in the geological history, all the land masses on the earth were joined as one single landmass. This landmass Wegener called as Pangaea. And he said this landmass, Pangaea, was surrounded by a water body that is Panthalassa. Okay, Pangaea, pan, German term, pan is all. जैसे pan India हम बोलते हैं, all India. So pan and Gea, G refers to ground or land. So Pangaea meant all land. Likewise, Panthalassa meant all water. So then he says that somewhere around 250 million years ago, 200 to 250 million years ago, this is the time when Pangaea broke into two parts. Pangaea breaking into two parts, the northern part he called as Laurasia, the southern part he called as Gondwana land. So the resultant looked something like this, Laurasia, Gondwana land. Laurasia is also called as Angara land. So Angara land or Gondwana land, Angara land and Gondwana land. And in between them, the space that was created, that was filled up with the waters. And that is what has been termed as Tethys Sea. So the arrangement in earlier arrangement after the breakup of Pangaea was Laurasia and Gondwana land separated by Tethys Sea. And after that, Wegener says that these land masses started moving. So over here, what are the things I have to know is first thing, as they were moving, the direction of movement. So direction of movement was first towards west and second away from poles. Now direction of movement towards west and away from the poles, for this he has told us certain forces. What were the forces responsible for this type of movement? So when we say moving towards the west, that he attributed to tidal force. And what is this tidal force? Tidal force is gravitational pull of sun and moon. So as the earth is rotating from west to east like this, so if I see this particular part and it is moving like rotating like this, west to east, or sun यहाँ पे या moon यहाँ पे है, so as it moves like this landmass would be pulled over here, gravitational pull. So that's where pull towards the west. Called it tidal force because this is the force which is responsible for tides in the ocean also. Gravitational pull of sun and moon. So for the westward movement, the tidal force, and for away from poles movement, he called it pole fleeing force. Pole fleeing force was mainly due to the gravitation. Because Earth does not have a regular shape. Oblate, spheroid, it is gravitational field at different places are different. And from that differences or variations in the gravitational field, the pole fleeing force is generated. So these were the two forces and the direction of movement. Along with that, braking के लिए he used centrifugal force. Centrifugal force. What do we mean by centrifugal force? Yes, anyone? Centrifugal force?
Outgoing force.
Outgoing, or how should I put it?
Away from the center.
Away.
Outward force, not outgoing, outward
Yeah,
force.
outwards.
Force acting outward. What is the opposite of centrifugal force?
Centripetal.
Centripetal. Centripetal is inward. So here, as the earth is rotating, centrifugal force. और लैंड मास है अगर इस पे सेंट्रीफ्यूगल फोर्स लग रहा है हर डायरेक्शन में रेडियली आउटवर्ड तो स्ट्रेच होने लगेगा ब्रेक हो सकता है दैट इज वेयर फॉर द ब्रेकिंग ही यूज्ड centrifugal force. For the movement he used tidal force and pole fleeing force. ये पहली बात है forces की. And so this would be your next question. Question mentioned there in the question list. Question में लिखिए direction of movement of continents and the responsible forces. And the responsible forces in the brackets mentioned there CDT, continental drift theory. Okay, next question mention कीजिए यहाँ पे. Next question. Timeline of Pangea and its breaking. Timeline of Pangea and its breaking. So timeline of Pangea and its breaking. Can see over here. 250 million years ago, this was when Pangea existed. Breaking of Pangea occurred around 200 million years ago. Under the question itself, you can just mention this. Existence of Pangea, 250 MYA. Million years ago, we write it like MYA. 250 million years ago, existence of Pangea. This period is called as Permian period. Permian period. Permian period, and breaking of Pangaea is 200 MY. 200 MY Triassic period. Written, everyone? Now, just check this diagram quickly. Okay, what's happening over here? Pangaea. In case of Pangaea, now you see an important point would be the location of India. India located over here near the South Pole. After that, the breaking occurred 200 million years ago. इसके बाद फिर further breaking started. You can see India now. India has moved from here to here. Further has moved from here to here. Along with that, another important thing that has happened is this part, which is most important in proving CDT. That is, this is the part of Laurasia. This is part of Laurasia. Let's say L1, L2. This is Gondwana land G1, G2. यहां से क्रैक आया फिर. And as they started separating, I can see this particular part coming up. ये देखिए from the, this is L1, this is L2, this is G1, Gondwana land 1, Gondwana land 2. तो as they split, यहाँ पे gap आया, which effectively resulted in formation of what? Atlantic Ocean. Correct. So Atlantic Ocean recent formation है. जबकि this was Panthalassa. So this is Panthalassa, and in the present time, what do we call this body as?
Pacific Ocean.
Pacific Ocean. So Pacific Ocean, Atlantic Ocean, if I compare, okay, I'll say that Pacific Ocean is nothing but primitive Panthalassa. Whereas Atlantic Ocean is a new formation. इसकी age definitely is less than 200 million years ago. Okay, new formation है. इसी तरह Indian Ocean भी new formation है. तो Panthalassa I can identify with present day Pacific Ocean. और इसके बाद with all the movements I have got these different continents in the present time. ये movement of the continents, how it occurred. So in these cases, what Wegener has done is Wegener gave related to continental drift theory. 1912 में this theory came out, or he formulated the theory in 1912, and the evidences related to continental drift theory. अब ये next important question है for the examination. Why I am saying so? Because mains में this question already has been asked. So in part, UPSC has a tendency to ask the question of mains in part in prelims also. So when we say continental drift theory, now continental drift theory ke evidences, when we talk about evidences, mein first evidence that comes up, okay, all this list is given anyways in your handout. So first is glaciation evidence. Glaciation evidence में in this whole region. So if I mark it over here, in this case, in whole of this area, right there from here to here. Okay, this is where the evidences of glaciation has been found. What I have marked right now, okay, lies over here, lies over here, lies over here, lies over here. Correct. This is, if you compare first diagram with the last diagram, this is the part we are talking about. Ab in the present time, if you see, all these locations are tropical locations. Present time का map देखिए आप, तो ये है tropics, tropical location basically. So all of these are tropical locations where glaciers cannot be there. but yet we have found the evidences of glaciation. कैसे मिला? Evidences of glaciation is related to something called as tillite. Till or tillite, it is the residual deposition of glaciers. जैसे रिवर्स के केस में हम क्या कहते हैं उनको? सेडिमेंट्स कहते हैं, एलुवियम कहते हैं, सेडिमेंट्स, एलुवियम. ऐसे ही in this case now we call these depositions from the glaciers as a till or tillite. So till or tillite we have, which are the glacier residual depositions. So in all of these regions they found tillite deposition. Explaining this is quite simple, क्योंकि if I see all these locations of the present time, if I go back to Pangaea, I find कि यहाँ पे all these locations in fact were near the poles. And as a matter of fact, you will have to know this particular fact, you will note down this fact that during the time of Pangaea, South Pole was located in Africa. Present time में South Pole कहाँ है? Antarctica पे. At that time, South Pole was in Africa. So during Pangaea, South Pole was in Africa. So quite understandable कि यहाँ glaciation था, क्योंकि all of these are those polar location. हाँ, yes, Aryan, please.
Sir, is it the magnetic South Pole or geographical South Pole?
It was geographical South Pole.
Okay.
In terms of climatic regions, we are defining them. ठीक है, मैग्नेटिक होने से तो ग्लेशिएशन पे कोई फर्क पड़ना नहीं है.
Yeah, that's why I asked.
हाँ. So this is the first thing. Got it, everyone? Apart from that, the second evidence, important evidences I'm just talking about. Second evidence is paleontological. Paleontological means fossil evidences. Paleontological evidence. A paleontological evidence may, you can see this particular picture that we have used over here. So if you check this picture of paleontological evidence, what are the different fossils that we are discussing? The first and very important one that we have to know should be that of Mesosaurus. Mesosaurus fossils you can see distributed across what region? Across South Africa and South America. Chile, Argentina, and then you have South Africa. Mesosaurus fossils यहाँ मिले, far away places. Okay, इसी तरह next one that you have to know is Lystrosaurus. Lystrosaurus significant because from examination perspective because इसके fossils India में मिले थे. ठीक है, and Lystrosaurus distribution you can see Africa, Madagascar, India, Antarctica. And then we have a plant from that time called as Glossopteris. Glossopteris के fossils were distributed all across southern continents. ये सारे southern continents हैं, which were part of Gondwana land at that time. Laurasia you can see has not been shown in this diagram. तो इन सबको हम southern continents कहते हैं of that time. तो यहाँ Africa, Madagascar, India, Antarctica, Australia, all the southern continents, Glossopteris has been found. तो ये क्वेश्चन यही था कि प्रेजेंट टाइम में अगर हम बात करेंगे तो लुकिंग एट द प्रेजेंट टाइम, अगर मुझे मीजोसॉरस के फॉसिल्स यहां मिल रहे हैं और यहां मिल रहे हैं, तो हाउ कम सो फार अवे मीजोसॉरस फॉसिल्स आर फाउंड? और द सेम गोज विद लिस्ट्रोसॉरस. Okay, the distribution like this, or Glossopteris all across here. How is it possible? It is possible if I कंसिडर पैंजिया कि ये तो कंबाइंड लैंड मास था, तो पहले इन दैट केस this was the zone where Mesosaurus used to live, one single belt, and then it separated out. Correct? इसे कहते हैं paleontological evidence. So in case of paleontological evidence, what should I know? Should be the distribution कि Mesosaurus के fossils कहाँ मिले हैं, Listosaurus के कहाँ मिले हैं, Glossopteris के कहाँ मिले हैं. ठीक है. So next question just mention over there. नेक्स्ट क्वेश्चन में लिखिए डिस्ट्रीब्यूशन ऑफ पेलियोग्लेशिएशन. डिस्ट्रीब्यूशन ऑफ पेलियोग्लेशिएशन. एंड नेक्स्ट क्वेश्चन डिस्ट्रीब्यूशन ऑफ मीजोसॉरस, लिस्ट्रोसॉरस एंड ग्लॉसोप्टेरिस. Mesosaurus, Lystrosaurus, and Glossopteris. So these are next set of questions over here. Then we have some basic evidences. Basic evidences include the similarities in the types of rocks which were found over here, which means across Atlantic Ocean. In this case, eastern coast of South America, western coast of Africa. यहाँ के rocks जब study किए गए तो what they found कि the rocks have similarities. The rocks have same age. And no wonder ये पूरा एक single belt था. तो यहाँ rocks were of same age. After that, separated out. So similarities in the age of the rocks have been found, and the most basic of the evidence which was found was the coastal fit. यहाँ पे आप देखिए this South America is fitting into Africa. तो in the present time भी अगर हम shape देखते हैं तो if I take this South America over here, it would be able to fit over here. This has been called as the coastal fit evidence. So different evidences related to continental drift theory. Everyone understood? And lastly comes the criticism of this particular theory. So in the criticism of this theory, okay, the basic idea I have to know is Wegener was, the forces that Wegener suggested, those forces were not found to be sufficient. This is a tidal force है. Okay, sun and moon pulling, the gravitational pull of sun and moon, pulling the land masses and making them travel so much. Okay, these are heavy land masses. So the forces were not found to be sufficient enough. Pole fleeing force, ऐसे भी pole fleeing force has not been verified. So that is one particular criticism. So criticism, what is the criticism? Criticism is that Wegener was not able to explain the forces. And forces were not found to be sufficient. तो ये हो गए criticisms आपके. And this is continental drift theory that you have to know about. Okay, so probable questions already I have told you from this. What can be asked over here? From here, now once continental drift theory came, 1912 came out, in 1920s when it was translated into English, criticized, discarded. ये पूरा एक life cycle है continental drift theory का. Okay, but post Second World War, a number of explorations and all were undertaken, and new findings started revealing new facts about the crust especially. Most importantly, जो ocean exploration हुए, deep ocean explorations हुए, So deep ocean explorations started revealing a lot of new facts about the oceans or ocean floor. And based on that, a geographer known as Harry Hess. Harry Hess came up with this magnificent theory called as seafloor spreading theory. Seafloor spreading theory. Okay, so seafloor spreading theory. Now, what was this seafloor spreading theory? Overall idea that Harry has proposed has been, if I want to understand it from the diagram. So if I take up this as continental crust, there is another continental crust over here, and I have a oceanic crust over here. Now, continental crust is thick and oceanic crust is thin. We understand this. That's why this diagram, thick, thin. Correct? Now, in this case, what we see, so this is the ocean, and I have the oceanic crust. Now, prior to Harry Hess, another geologist or geographer named as Arthur Holmes proposed this concept of convection current. तो पहले ये convection current समझ लेते हैं इसके लिए. In short, what Arthur Holmes proposed was that if this is the earth, हमने कहा asthenosphere में the material is in semi molten form. मतलब यहाँ melting तो हो रही है. And in the mantle, especially upper mantle में, there is a lot of heat that is trapped, due to which meltings happen. Now, if the melting of the rock is taking place, rock melts over here. Okay. As the rock melts over here, और यहाँ पे बाकी rock solid है, ये सब solid है, and at this particular location, the rocks have melted. Very obviously, as it melts, its density becomes less. It becomes lighter. And as it becomes lighter, it is going to rise. It's absolutely like the working of hot air balloon. Hot air balloon mein, what are you doing? You are heating the air over here. As you are heating the air over here, the air becomes light. And so air starts rising. क्यों air starts rising? Air starts rising क्योंकि यहाँ पे जो air है पूरा, इसमें this parcel of air has become heated. So this has become lighter than the surrounding air. ये heavy है. So it starts rising. Hot air balloon. Similar to that here, this is a heated material, molten material. It starts rising from here. And underneath the crust, it spreads out. Eventually, as this is rising and as this is spreading out, it is constantly losing heat. Correct. अब आप सोच के देखिए again, what you do is a hot air balloon you are using, you heat it just over here and leave it. The air will rise, but will it keep rising? No, क्योंकि आपने air को यहाँ heat किया है. As the air goes up, it is constantly becoming cold. और एक टाइम पे ये cold हो जाएगा. तो अगर आपको, if you have to keep hot air balloon floating in the air, what do they do? Constantly heating the air. तो वहां they use fire in the hot air balloons. यहां पे देखिए तो is it one time heating or constant heating?
Constant heating, sir.
नहीं, one time heating चाहिए.
Okay.
The rocks melted here. That's it.
Okay, sir.
After that, the heated material is just moving. So will it remain hot or it will keep cooling?
It will keep cooling then.
Keep cooling, क्योंकि यहां जो rocks हैं, they will be taking heat from here. So it will keep cooling, and so as it spreads, it will become colder and colder. Or by, let's say, by the time it reaches here, it has become cold. Correct? Now, if it has become cold, it will become denser, क्योंकि उसकी original density तो यहाँ की थी. And if it has become denser, what will happen? It will start descending back to its original location, जहां जाके वो फिर से solid हो सकता है. But this process keeps happening. And this is what we call as convection current. Convection refers to vertical movements. तो यहां convection current. So again, the same question जो पहले हमने किया था कि source of heat for asthenosphere. हम इसको अलग तरह से पूछ सकते हैं, source of heat for convection current. What would be these sources?
Radioactive material and
Radioactivity and
stored heat of Earth.
residual heat.
Residual.
Radioactivity and residual heat. तो कन्वेक्शन करंट के सोर्सेस भी यही हो जाएंगे. सो कन्वेक्शन करंट सोर्सेस, इसको नेक्स्ट क्वेश्चन लिख लीजिए. कन्वेक्शन करंट सोर्सेस. And put a hyphen and just mention radioactivity and residual heat. So Arthur Holmes gave this idea. Okay everyone, वहीं जहां क्वेश्चन आपने लिखा है ना, वहीं put a hyphen and mention Arthur Holmes, तो क्वेश्चन में ही आपको दिख जाएगा. Arthur Holmes gave this idea. Now Harry Hess used this idea in seafloor spreading. अब what Harry Hess says, everyone see here. For Harry Hess, he argues कि somewhere underneath the oceanic crust, some convection currents would be present, because convection current is present everywhere on the earth. तो मान लिया कि there is convection current present over here, जहां से convection current rise हो रहा है. ठीक है, it's the same convection current what was proposed by Holmes. And now after this material will be moving out. This is precisely convection current diagram. Ha, yes, Minit. CDT was explained without the concept of convection current. Absolutely. तो CDT 1912 में आया था. convection current और ये 1940s 50s इस टाइम पे all these concepts came. तो यहां पे convection current assume कर लिया हैरी हेस ने. अब what would be the result of this convection current? देखिए यहां पे due to this rising limb of convection current, there would be a pressure on the oceanic crust, and oceanic crust is thin. So what happens? Oceanic crust ruptures from here, break from here, which results in magma coming out, और ये magma यहां solidify होता है. Magma solidifying over here, this will result in a sort of mountain, जैसे volcano होता है. This mountain, now this is called as mid-oceanic ridge. MOR. Mid-oceanic ridge. Ridge means mountain. Mid-oceanic ridge. तो यहां mid-oceanic ridge form हो गया. Apart from that now, the oceanic crust has been broken into two parts now. One part here and another part here. And just underneath these broken parts of oceanic crust, I have these convection currents moving. It's like a river flowing and on the top of that something is kept. So it will push the oceanic crust also in this direction. अब at this point क्या होगा? The oceanic crust will start pushing against the continental crust. Correct? So it would be like continental crust, oceanic crust. Oceanic crust is pushing against the continental crust like this, moving from here and pushing it like this. But out of these two crusts, which one is heavier and denser?
Oceanic crust.
Oceanic crust. Oceanic crust is heavy and dense. And as such, oceanic crust is pushed downwards like this. Okay, this process is called as subduction. Now, the result of subduction is because it is pulled downwards, यहाँ पे एक depression form होता है, and this depression is called as trench. The depression is called as trench. Along with that, the sediments which were present on the ocean floor, these sediments also go down, and due to high temperatures in the depth, these sediments melt. And as there is melting of these sediments, अब ये sediments is interior origin or surface origin? Sediments.
Surface, sir.
Surface. Sediment तो surface से आए हैं. ये crust जो है ये तो यहां से आ रहा है, इसका solidification हो रहा है. तो oceanic crust was actually sourced from here. लेकिन sediments तो surface origin है, मतलब lighter है. So as it melts, it is very light, and so it starts rising and comes out over here in the form of volcanic eruption. Yes, got it, everyone? So here I get volcanic eruption, and precisely the same phenomena is going to happen on this side as well. The same phenomena on both the sides. This is the idea of seafloor spreading. So now in seafloor spreading, what are the types of questions that can be asked from this particular arrangement? इसके बाद हम बाकी बातें करेंगे अभी. Okay, but first the arrangement which is there. So from this arrangement, one question would be related to the subduction aspect. कि continental or oceanic crust में which one subducts? That is oceanic crust. So next question you mentioned there. Next question would be related to which crust always subducts? Which crust always subducts? Answer would be oceanic crust. And next question, continental crust never subducts. Next question is continental crust never subducts. Why? What can be the reason?
Because it's lighter.
Absolutely, because it is lighter than the underlying material. इसके नीचे जो मटेरियल है वो डेंसर है, कॉन्टिनेंटल क्रस्ट लाइट है, एंड आर्किमिडीज प्रिंसिपल हमें बता रहा है लाइटर मटेरियल तो ऑलवेज फ्लोट होगा. सो इट इज प्योरली आर्किमिडीज प्रिंसिपल. So continental crust can never subduct. Under any condition, it will not subduct. Always oceanic crust will subduct. हाँ, yes, Nivedita, please.
So when we are saying these volcanic eruptions which act as a direct source to the sources of studies, So these are only in that aspect that the change in nature after the subtraction that we
Yes,
are studying only
absolutely.
that only.
Not just that, this is only one form of volcanic eruption. It's not always that every volcanic eruption will give you complete idea of the interiors of the earth. Because in this case of volcanic eruption, majority of the material is nothing but molten material of the surface only, sediments. But volcanism has a number of different aspects. In case of divergent boundaries also, when we study plate tectonics, there also the volcanism will occur. So different types of eruptions will give you different ideas. This specifically will not give you almost every idea about this depth, क्योंकि यहाँ melting of sediment is taking place, not of the crust. So this was your question. Now, apart from that, what I see, the next question just mentioned there again, formation of new crust and destruction of old crust. Formation of new crust and destruction of old crust. So formation of new crust, where is it happening?
Mid-oceanic ridges, sir.
Mid-oceanic ridge. This is where new crust is being formed. क्योंकि crust formation का मतलब है कि magma has solidified, become rock. यही crust formation है. तो यहाँ पे there is a new crust formation that is taking place. Destruction of old crust कहाँ हो रहा है? Trench पे. Because the old crust is going down. So that is the destruction of old crust. So what were the evidences that were used to prove seafloor is spreading? The evidence basically is with respect to age of the rocks. Age of the rocks अगर हम यहाँ पे बात करें तो age of the rocks location X and location Y. Where should I have older rock?
Why?
Location Y.
At location Y, because location X पे it is forming and then it is moving. That's why it has been called as a conveyor belt system. यहाँ फॉर्म होता है रॉक, उसके बाद यहाँ ट्रेवल करता है और फिर सबडक्ट. तो very obviously as you move from here to here, the age of rock is going to increase. Near the MOR you find younger rocks, near the trench you find older rocks. Same goes with the sediment deposition also. New crust पे sediment deposition कम होगा, time factor. And this crust let's say is 500 million years old. तो यहाँ पे crust आपका इतना थिक, ये sediment इतने थिक हो जाएंगे. The age of the rocks as well as the thickness of sediment on the ocean floor both increases moving away from MOR. Age of the rocks भी increase हो रहा है, thickness of the sediment भी increase हो रहा है. Yes, everyone understood this part? ये है evidence. इसके बाद another interesting evidence was the magnetic patterns on the ocean floor. So magnetic pattern on the ocean floor, what was found has been, if this is the MOR, MOR, on the either side of MOR, they found the rocks to be arranged in patterns like this, which had magnetic polarity preserved as north-south, south-north, north-south, and likewise the same symmetric pattern over here. Okay, this has been called as magnetic anomaly. Magnetic anomaly. So why magnetic anomaly occurs? Magnetic anomaly occurs due to two facts. One, that is seafloor is spreading. seafloor spreading, and second due to pole reversal of Earth. Pole reversal of Earth. Which means over here, pole reversal, when you say, it is basically when the magnetic poles of the Earth, okay, they keep reversing their position. जैसे अभी यहां नॉर्थ साउथ है, आफ्टर अ वाइल ये साउथ हो जाएगा, ये नॉर्थ हो जाएगा, मैग्नेटिक पोल्स की बात कर रहे हैं. फिर आफ्टर सम टाइम इट विल अगेन चेंज, and this is a very common phenomena on the Earth. But I have to understand that every time this pole reversal will happen, the new solidification that would be taking place here, that will acquire that polarity. तो हर बार जब भी पोल चेंज होगा, पोल रिवर्सल होगा, नए रॉक्स जो बनेंगे, they will have a different polarity. And that's why you have these strips. Now, these strips are very, very useful for geographers. Why? Because scientists, geographers, what they do is, by counting the number of strips, they can precisely tell the number of times pole reversal has occurred. यहां इस डायग्राम को देख के I can tell how many times pole reversal has taken place.
3 times.
3 नहीं, 2 times. पहले नॉर्थ साउथ था, वहां से एक बार साउथ नॉर्थ हो गया, और फिर से एक बार ये हो गया. 2 times चेंज हुआ. तो if you count the number of strips, okay, you will be able to tell the magnetic history of the Earth. Correct, everyone? Magnetic anomaly. So these are the evidences related to seafloor spreading. अब इससे related बहुत interesting facts आते हैं कुछ prelims के लिए. What is one fact कि अब अगर हम बात करें अर्थ पे ओशियानिक क्रस्ट और कॉन्टिनेंटल क्रस्ट की, तो which one should be more older?
Continental, maybe,
And why is it so?
as oceanic crust undergoes again and again reformation. Continental crust
Absolutely.
never undergoes.
Absolutely. So next question for you, mention there. Continental crust is way much older. Continental crust is way much older than oceanic crust on the surface. Than oceanic crust on the surface. Why? ठीक है, इसका आंसर होगा कॉन्टिन्यूस डिस्ट्रक्शन एंड रीजनरेशन ऑफ ओशियानिक क्रस्ट. तो ओशियानिक क्रस्ट होंगे पहले से, नो डाउट इन दैट, लेकिन एस्पेक्ट यह है कि ओशियानिक क्रस्ट डिस्ट्रॉय भी होते चले जाते हैं. बट कॉन्टिनेंटल क्रस्ट का तो हमने बोल दिया कि सबडक्ट होता ही नहीं है. अब अगर सबडक्ट होता ही नहीं है तो देयर इज नो क्वेश्चन ऑफ डिस्ट्रक्शन ऑफ कॉन्टिनेंटल क्रस्ट, वो तो रहेगा. तो दैट्स वेयर ओशियानिक क्रस्ट बहुत यंग है, जहां भी देखे जाएंगे, जहां भी मिलेंगे. ओल्डेस्ट ओशियानिक क्रस्ट कहां मिलना चाहिए मुझे?
पैसिफिक ओशन.
पैसिफिक ओशियन में, क्योंकि वही प्रिमिटिव या प्रिमिवल पैंथालासा है. बाकी तो बिल्कुल रिसेंट बने हैं, इंडियन ओशियन हो गया या अटलांटिक ओशियन हो गया. तो ये डिराइव्ड फैक्ट है. ठीक है, तो एज ऑफ द क्रस्ट पे आपको क्वेश्चन पूछा जा सकता है, बहुत इंपॉर्टेंट है. Everyone understood this? Last thing about this is the forces responsible. Forces responsible, although this particular aspect of forces responsible, this we use in plate tectonics also. The fact remains same. So forces responsible, the first force is applied by the outcoming magma. तो जब मैग्मा यहां से it forces itself out, it pushes this crust outwards. ये first force है, and this force is called as ridge push force. Ridge push force. Second force which is there is where the magma is flowing underneath. Correct? A molten material convection current is flowing underneath, and as it flows in this direction, it drags the plate, drags the crust along with it. And so the second force that is there, this is called as dragging force due to convection current. Dragging force due to convection current. And the third one is where this slab is going down. And so gravitation will start working on it. Correct? And as the gravitation starts working on it, it is pulled down like this. And as it is pulled out down like this whole portion is pulled like this. And so this third force, this is called as slab pull force. And out of these three, this one is strongest of all. Slab pull force, this is the strongest of all. So this for us now is seafloor spreading concept. Okay, everyone good with this? So for this session now, 3 topics we have done: interiors of Earth, continental drift theory, seafloor spreading. How many questions you have written till now? If anyone is numbering it?
19, sir.
19. So 19 questions precisely, you know, what can be asked. This would be how you are going to revise it. So that's for the first session. Okay, let's meet at 1 p.m. for the second session. Okay, see you after an hour.